Hi all, in this video I'll be guiding you to chapter 4, chemical bonding. Next week in class we'll be looking into subtopic 4.1. Therefore let's use your lecture notes to follow through what we are going to learn. So in this video I'll be focusing on just stating the octet rule as well as how ions achieve stability by attaining stable configuration via noble gas, pseudo-noble gas configuration and half-fill orbital configuration. That's about it. Alright, so let's get started. Now, when we talk about chemical bonds, it is actually the force of attraction that holds the atoms together in a new species or a compound, right? It involves only the outermost orbital or the valence electron, and we have three types of bonds that we are going to cover throughout this chapter. So first would be ionic bond, covalent bond, and under subtopic 4.5 we will be covering the metallic bond. Okay, so let's focus on ionic first for this video. So as you can see over here, they have highlighted what is a valence shell, what is an outermost orbital, all right, and the valence electrons. So quick recap on what is an ionic bond. Definitions are important. So ionic bond is an attractive electrostatic force between a positive and negative ions, whereas for covalent bond, it's the electrostatic force of attraction between the shared electron with the nucleus of both shared atom. All right, so let's get moving to ways that we can draw electrons surrounding our element. Okay, we have drawn using shells in SPM. Now we want to make it better, so we use Lewis symbols. I would say make it easier. All right, so Lewis symbol, okay, as you can see in the left, is a symbol of an element in the middle, and we represent with a dot or cross for each valence electron. So this is actually going to make your life easier. You don't have to start drawing all the electrons like you did in school. Like you draw the first shell and then you draw the second shell and so on. So we don't have to do it. We only focus on the valence electrons. All right. So these are the general valence electron configurations. As you can see over here for group 1, group 2, group 13, 14, 15, 16, 17 and 18. And for this chapter, we will be mainly focusing on S block and P block elements. Alright, so now let's look at period 2 and its counterpart in period 3. So group 1, lithium, we know that. So lithium has got one valence electron and that's it. You put a one dot over there. I would prefer you using the dots first compared to cross. Alright, so we are going to do dots mainly. Okay, so sodium, beryllium, magnesium, boron, aluminium, carbon, silicon. Now I want you to take a look how they progressed with the dots. Okay, they started off with left and then you go right and right, left. Okay, I would say kiri, kanan. And then we go atas and finally we go atas, bawah. All right, so when you want to distribute electrons beyond 4, same thing. You start with one of the sides. So in this case, they start on top and then they go down. Next, they go left and then they go right. Okay, so you can do atas bawah kiri kanan or kiri kanan atas bawah lah. Alright, I would always go with kiri kanan atas bawah. Somehow I like it like that. So this is how you draw Lewis symbols for atoms. Okay, right. Next, let's go on to the octet rule. So we know this term octet. It's not a new term. So octet rule states that molecules and polyatomic ions, okay, What are molecules? Let me draw an example of molecules over here. Simple molecule would be H2O, or your methane, or your ammonia. So these are all molecules. And what about polyatomic ions? So polyatomic ions would be just your sulfate, your nitrate, or even your carbonates. So these are all polyatomic ions. They have the tendency to maintain or to have 8 valence electrons surrounding each atom. Okay, so this is to achieve noble gas configuration, and we know which is stable. I think in SPM you would have written it as stable octet electron configuration or electron arrangement. So here we focus on the term noble gas electronic configuration. However, we also know some elements like hydrogen, they can't achieve 8, so they achieve 2 electrons in their valence shell. So they now are duplet, okay, which is also stable. Let's go on. So how can we achieve this octet rule? So we can achieve via 2 ways, which you have to know, by transfer and sharing. So transfer is going to result you in the formation of ionic compounds, and sharing is going to result you in covalent compounds. You're going to make covalent bonds, so you're going to get a covalent compound. Here you're going to make an ionic bond, therefore you get ionic compounds. Alright, so here when we want to show pembentukan ionic compound ni, tak perlu dah lukis petala. You just transfer the valence electron from lithium to fluorine as shown. And this part I think it's the same lah without the petala. Okay, and the configuration for each ion is written at the bottom. Now what about sharing of electrons? We don't show any arrows, okay? We no more show petala, we don't show shells. We just arrange them so that in the middle we have a pair of electrons shared. So when you have a pair of electrons shared, that means you are forming a single bond. Alright, so a single bond, and you can draw your lone pairs surrounding it. Okay, here I would like to introduce a term. Okay, I'll be repeating this in class, the term, but I think we can get started with it. So can you see this pair on top of fluorine? We call them as lone pairs because they are not involved in bonding. Whereas these 2 electrons, which I have highlighted in the middle, we call it as bonding pair electrons. Okay, these pairs above fluorine, okay, that's actually 1 pair, 2 pair, and 3 pair. These are lone pairs, whereas the 2 electrons in the middle, we call them as bonding pair electrons. Alright, let's get going. So now we will be focusing on ions. Alright, just here. Let's bring this here to the next slide. Stability of ions. Now, ions are generally stable because they have noble gas configuration. That's what you have learned in SPM. Okay, because they have valence electron 8, so it matches a noble gas configuration. Next, additionally, you have to know there's also pseudo noble gas configuration. So pseudo, what is this word pseudo? Pseudo means mirip. Okay, pseudo noble gas configuration. And finally, we have been learning a lot about this half-fill orbital, and that is also a stable configuration. Okay, we know half-fill orbitals have extra stability, therefore that can be also made into a configuration. Right. So first example, formation of stable ions via noble gas configuration. As you can see, noble gases have general configurations of NS2 and P6. So for example, if I take sodium and make it into sodium ion, it will be 1s2, 2s2, 2p6. That is the same as neon's configuration. So that's why the first form of stability in ions, we say it has noble gas configuration. Same goes to fluorine over here. As you can see, fluoride receives 1 electron, and there you have it. The configuration matches of neon. So we have few elements in our group 18. For example, we have got helium, we have got neon, we have got argon. So if the ions configuration matches this element's configuration, which are your noble gas, we say the stability of ion is achieved via noble gas configuration. Okay, next, pseudo-noble gas configuration. So for pseudo-noble gas configuration, you can narrow down your options to focus on transition elements. All right, and transition metals. So transition elements, as we know, it involves the d orbitals. So when ions are formed, the d orbital is fully filled along with the p and s. Okay, so when you have a fully filled orbital, but it's not the same as noble gas configuration, we still have to classify it to somewhere, right? So that would be a pseudo mirip noble gas, pseudo noble gas configuration stability. All right, because we have also learned in the last chapter, when you have fully filled, the term here is when you have fully filled orbitals, they have extra stability. So we have to acknowledge that. What do? We claim it as pseudo-noble gas configuration. All right, so we have two examples over here. You can have a look. Copper, when it forms Cu+, the valence orbitals are all fully filled with electrons. Therefore, it has a pseudo-noble gas configuration. And finally, we have half-filled orbital. We saw this clearly in the formation of Fe3+. And here, there's another example, Mn2+. All right, so Mn, it had 1s2, the configuration was 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, 4s2. All right, so remember, when we fill up 4s2, we fill up first, and then it goes higher in energy. Therefore, during the formation of ions, we remove the 4s first, resulting in a half-filled 3d orbital. Half-fill is exactly 3d5, and it has got extra stability. So we have to acknowledge that. So we give a name for it. It's half-fill orbital configuration. So that's the third type of stability experienced by ions. Okay, I hope a brief introduction would help you prepare for next week's class. Thank you.